welcome everyone to today's TEWI-Kolloquium, and our guest today is Toni from UCL University College London. She received a master and PhD both in electrical engineering from University of Bologna, but also had lots of visits outside. Was a visiting scholar, for example, at the University of California in San Diego, and also was a postdoctoral fellow at the same university in California, and also at the EPFL. And now is a lecturer in electronic and electrical engineering department at the University College London. Her research interest mainly involves the interactive multimedia systems, decision-making strategies under uncertainty, large-scale signal processing, and communications. And today she will talk about understanding users' behaviors in user-centric immersive communications. And the floor is yours, Laura.
Thank you, Kristen, so much, and thanks for the invitation. Thanks for already introducing the topic. I will go straight to first thanks the people that are behind the work that I'm presenting today. So today I'm presenting the work that most of, we know the efforts has been done by the PhD students. So in my case, it's Silvia Rossi, who has contributed to this work. But we also had many collaboration with Trinity College, with Charlie Odznar and Alyosha Smolic, but also with Pascal Frossard PFL and Francesca De Simone when she was at CWI. So today I'm going to present a little bit a summary of the works that we have done together with all these researchers, mainly focusing understanding the user behavior while they experience VR content. And before going into the details of the contribution of my work, let me just give you some sort of context and main motivation. So I guess most of you are already familiar with the immersive and interactive communication that we have experienced and we are going to experience later on. So virtual reality, 360 degree, in which we can navigate, or also a sort of possible augmented reality. These are very, very interesting application, and this is, I think we are seeing just the beginning of it. But there are many challenges already behind. So for example, for virtual reality in 360, we have a new spherical geometry as a format of the dimension. We also know that the volume now is huge. So what we have to store, to compress, and to deliver is massive. But at the same time, you also want to interact with the content. So we also want to have huge ultra low delay in situation in which bandwidth is not infinite. And at the same time, everything is a function of the user, because it's the user who is interacting with the content. But this interactivity gives uncertainty on what the user is actually going to ask. So all this create many challenges, and they can, at least our vision is that they can be solved or approached by trying to have a personalized coding and streaming delivery chain. So really putting the user at the center of the whole pipeline that we have. And there are already few works that have many works actually that are going toward that direction. So how, for example, the adaptation logic in an adaptive streaming can be adapted to the user behavior, how can anticipate and predict the user behavior and try to maximize the quality of the content that the user will actually consume. And at the same time, also the coding part can be optimized knowing a little bit what is going to be the user behavior. But as you can understand, because I already mentioned it a few times, it's all about understanding and anticipating the user. So what type of content will I be consuming and where I will be looking at. And for example, in the kind of, this is a kind of pipeline that could be seen as an adaptive streaming with a content provider, a network, a CDN in the middle, and then a user posing HTTP request for downloading the content. If we could have an anticipation of what the user is going to look like, or which portion of the content the user is going to request, we could try to have that request at high quality and the rest at low quality, for example. So this is one simple way of trying to show how we can save bandwidth but still preserve the quality of the user. And it's all about understanding how do users behave in the virtual environment, and if we can anticipate and predict this behavior. So this is the core of today's talk, that is, how do users actually navigate in the virtual reality environment. And today I'm mainly focusing on 360-degree video. So when I have, for example, an headset device, when I move my head, of course, I change content and I create a trajectory. So can we understand this behavior and can we predict it? Specifically, the questions that we are going to address is, can we identify key patterns across all the possible users? Do we have some dominant ones? Can we understand if users actually share some similar behavior? And I'm going to tell you later why this might be important. Or can we understand if some users are more predictable than others? Can we see kind of the virtual trajectory as a signature of each possible user, or can we classify users depending on their behavior? And of course, the other aspect is also toward the idea of predicting is, do we also know whether this behavior is affected by the content, by the view in the device, or any type of other factor? And this is very important, or at least we started this direction to kind of optimize the whole pipeline of coding and delivery. But we found out that, of course, there are many other applications, and especially the ones that we have some initial discussion, but it's really preliminary, is also, can we have this analysis of user behavior more for a metric, a quantification way, so a really quantitative rather than qualitative way? And can we use this also in therapies that now have started to be there in the VR settings? But these VR settings therapy now really don't have a quantitative metric to assess patients. So can we actually translate into that? And at the same time, can we also translate into understanding user emotion in more from an audience in the case of live performance? So it's something that it's interesting to see that is not only for the pure optimization chain of the streaming, but it can also be applied in many other scenarios where there is really the need to quantify the behavior of the users. Okay. In terms of main contribution, let's see a little bit. I already anticipated this. So our main goal is to design metrics and methodology that allows us to analyze the user behavior in 360 content with key factor or key goals, sub-goals of trying to understand if there are dominant behaviors or dominant trajectories that the user perform, trying to understand if we can analyze and quantify the similarities on how users perform these trajectories, and also the level of interaction. I'm going to mainly subdivide these sub-goals in three main topics, kind of all correlated, but one is the first clustering approach that we proposed. A deeper analysis, also trying to have more an idea of content and viewing device effect, and a use case application in the dash streaming or adaptive streaming aspect. And then a formalization of further metrics that can be used in this type of analysis. In terms of why we need that, people that are working on that could argue that already there are many data sets available and many analyses that have happened in these data sets. So indeed, there are already many metrics, and there are many ways to try to analyze the behavior of users. What we found is that sometimes there is a lack of analyzing the user behavior, looking at the full trajectory, so the actual behavior over time, rather than the single frequency of fixation or other type of analysis. And also, let's see if this video clarify the difference between looking at the trajectory and maybe an heat map. So you might have two scenarios, and in some, these blue points, for example, sometimes they jump from one cluster to the other, but not so much. While these other greens were jumping more from one scenario to the other. But at the same time, if you look at the sort of what could be the heat map, okay, now it has started again. If you look at the heat map, you could still see that more or less it tends to be similar to the scenario A heat map. And that's because maybe even if user were jumping from one direction to the other, the amount of time in which they were in these two areas was more or less the same. And that's kind of just an intuition to show why I think it's still interesting to have a deeper analysis of the trajectory and the exploration that you do over time. And on the top of that, there are also many metrics, but sometimes if you want to understand if users are similar one from the other, it's still not really easy to understand from the angular velocity or other type of metrics. So this is the main motivation. And let's see the first approach, that is the clustering approach. So I already anticipated that, but what do I mean by trajectory of a user? Well, it's a user that maybe with a headset or a tablet or any other type of device is looking at the 360 video content and is moving. So every time that you look at the 360 content, just let me give you this introduction for people that are not very familiar. This viewing device will actually display out of the whole spherical content only a portion of that we call viewport in this talk. And therefore this maybe T0 is the center of the viewport that you display at a given time. And then over time, you maybe move your head or move your tablet, and that the content that you display will change. And so you can establish a sort of trajectory that could be represented as the center of the viewport that you are experiencing, so that you actually view over time. And then you can have different users, therefore you have different trajectories. The first goal was very easy. Can we actually understand if what we can get from a clustering analysis, and can we use classical clustering, or do we have to improve the current state of the art? So we wanted to cluster them. Why? For many reasons. One is, for example, we want to find that there are some outliers, and we prefer to have heat maps or any other type of metrics established only on the core dominance behavior of the users. That's one possibility. The other one is that maybe we can try to understand that users that belong to one same clusters can then be used for prediction. So for example, we can build some prediction model, we can train the model only for users within that network, or maybe we can, if we have two users and a third one that actually seems to be very similar, we can try to assume that it will have a similar behavior to the other ones in the cluster. Another one is a practical way to understand the level of interactivity and how user behave in a data set. And this is what I will going to show you in the second part of the talk. Another one is sometimes I got people asking me like, I would like to understand, to assess the quality of experience of user within a given content, but there are many users, many trajectories. So it would be nice, for example, to identify the 3 dominant trajectories that people usually experience within this content. And that could allow me to say, just to identify the dominant QoE that is actually going to be experienced in the content. So that's also sometimes the reason, or if we want to optimize the coding, you can optimize it toward this dominant behavior. So you may sometimes also be willing to understand what is the dominant behavior. And rather than only the heat map, you may want to actually really looking at the dominant trajectories, because you may want to care about the quality variation also that is happening over time. So that's also what could give you this dominant behavior. There were many challenges that prevent us to use classical k-mean or other type of clusterings that are already adopted. The first one that, however, is what was easy to obviate is that, of course, we now have a spherical content. And what we know is that spherical content usually get projected into a bidimensional domain. And however, there is some deformation. This is just one type of projection. There are many others, but it's more to give you the concept that maybe points, so let's assume that these points are 2 centers of viewports. here it seems that they are at the same distance, but actually in the actual spherical domain they're not. So we just wanted to be careful to use a kind of metric like geodesic distance that reflect this spherical geometry instead of just looking at Euclidean distance on the b-dimensional domain. And then the other part is, how do we define a clustering meaningful? So our goal was at the very beginning to optimize clustering for fetching to the pipeline of adaptive streaming. So we really wanted to say that users are in the same cluster if they actually look really at the same content. So if the viewport that they're looking at is almost the same. So we wanted really to identify clusters that shares, or at least they have a good overlap of the viewport. And for example, the geodesic distance can actually be the same between these two viewports, but it's not including the rotation of the actual viewport. So as you can see, the overlap here is 87%, while in this sense, in this case, the overlap is 58%. So these two viewports, looking only at the center and the geodesic distance of that, you would assume that they look the same, but since the rotation of the viewport is different, the overlap is not the same. So an easy way is, yes, you can take into account spherical distances and just look at the geodesic distance of the center of the viewport, but that's not always an accurate proxy for the overlap of the viewport. So, and we wanted to have that. So we wanted to identify users that are actually sharing good portion of the viewport. And that's why, because just to give you an idea, and then I'm going to tell you how we did it, but if you have all these centers of user with all these viewports, maybe a k-means cluster could cluster users in this way, these blue and these red points. But if you look at these ones that are the two extremes of the cluster, the overlap between these 2 points is minimal. So you start to understand that maybe clustering can be easily done, but it might not always be meaningful. So we just wanted to have a constraint to ensure that. This is more for people that might be interested later in reading some state of the art. There are already few clustering analyses, but some of them really mainly look at the Euclidean distance rather than more spherical geometry aware metric. The one by Stefano Petrangeli and Gwendal and Vichy had already some very nice idea of looking at clustering, but more from a classical one rather than having an actual constraint on the overlap of the viewport as I just described. So we tried to see if that was actually important to preserve this overlap. So what we proposed is like a two-step clustering. In the first one is we're trying to finalize the metric that we want to consider. And then in the second one, we propose a clique-based clustering that I'm going to tell you later what it means. Just to tell you, we had a lot of geometric analysis and some of that is still going on. Here we just show you the first solution that was of course the easiest one that we picked, that we still have as a metric between two viewports. We still consider the geodesic distance between the two center points of the viewport, but we assume that we pose a constraint. So basically we wanted to pose a constraint on, as you can understand, if viewports are quite close by themselves, the rotation still matters in terms of how much the overlap changes, but not too much. While if they're quite far apart, whether they are like that or they are like that, the rotation might have a big impact on that. So we just wanted to understand what is the threshold value of geodesic distance above which we cannot guarantee an overlap of, let's say, 80%. So we just wanted to understand, and we did it with an ROC curve, but the point is really at the intuition level to say, okay, if you have two viewports, what is, can you understand a threshold value of below which you can say viewports that have the distance that is below this threshold, they usually have, in a probabilistic sense, 80% of the overlap between the viewports. And above that, you cannot guarantee that overlap anymore. So this is what we had, and we got a geodesic distance value as the one that kind of optimized the trade-off between true positive rate and false positive rate of this having a viewport overlap of at least 8%. And basically what we did is, based on that, given that geodesic distance, so we assume that users with a viewport that has a distance, a geodesic distance below the threshold, were kind of neighboring because they were sharing at least 80% of the viewport in terms of overlap, while others, they were not. So we kind of create a similarity map, kind of, between the users. And with that in mind, we could construct graphs in which all nodes are represented, each user is representing a node in the graph, and there is an edge if we have this condition. So if the overlap between these points is at least 80%. And that's it, because then we just applied clique-based clustering. That is, we're trying to ensure that we have an iterative process. The details are in the paper, so we skip it here. But it's more to give you the intuition that we impose that every clusters form a clique. So each element in the cluster are neighbors, so they have an edge going between them, which means that we ensure that all the users in the cluster share at least 80% of the viewport. So that was a little bit the first contribution toward this direction. This is the algorithm. I just wanted to go toward the results because I wanted to also have time enough to then go through the rest. But the point is that we consider the results here are for two main sequences that are a little bit different one from the other. The roller coaster is when there is a main subject that is the roller coaster and is moving, while time lapse is more a scenario of New York with people moving. So there is not the core focus of attention. This is a visual understanding for people that would like to understand what is the difference between a classical clustering and the clique-based one, in which we impose this constraint of overlap between the viewports. So this, of course, is the spherical content unwrapped in the bidimensional domain. And you might see that there are some users focused here, but then there is one user that has a trajectory that does like that still is incorporated in this cluster that is the orange one. But this is a kind of an outlier compared to the other guys here. And in our cluster is indeed considered as a single cluster. So it's not incorporated into this other cluster. So the point is that you have, of course, more single clusters, but you are sure that the core ones are really the user looking at the same core viewport and the same core behavior. This is just a numerical example to compare other state-of-the-art algorithm or classical clustering, and to show that actually, indeed, if you cluster with this clique-based clustering, you do have a high overlap that is about 80% with our proposed algorithm of the overlaps. So this is the overlaps of the viewports of users within one cluster. So we wanted to be sure that we reach that goal, that once we cluster users, we ensure that within a cluster users share really, they are looking at the same type of content. Basically, this is what you wanted to show. And this is the validation that indeed the clusterings are meaningful. And this is how we can use the cluster. So this, I think, at least to me, is the most interesting result is if you watch a video, so this is the time, and you basically plot here all the users, and the color represents the size of the cluster. So if users are within a cluster that is very big, it will be a red dot, a red square. While if users belong to a single cluster, it might be a dark blue. So at the very beginning, as almost experienced in all the VR environment, users are really scattering and wandering around. So it's very difficult to find key clusters. But what is interesting is that if you look at the whole video sequence, so if you go from left to right, you see that there are some red bands, vertical ones. So in that moment, it means that the content is such that all the users tend to behave the same and focusing on the same content, and therefore you can identify a key cluster, basically. So this is another way in which you can also use the cluster information. Okay, and that was the very first approach to this analysis. There are many questions. So on one side, we are improving the cluster. But what I'm going to tell you now is also, can we understand better this user similarity, kind of expand the results I just showed you now? And also, do we understand better which factor have an effect on this similarity of users or cluster results? So we wanted to see better this, and this is what we did in our second work, that is the one we did in collaboration with Trinity College Dublin. The very first question is, we had the cluster, we wanted to test it more. However, we wanted also to try to understand what is the effect of the user behavior of the viewing device on the user behavior. However, we noticed that most of the data set nowadays only use the headset. So we also developed, we basically ran a campaign to collect more data in which users were watching a 360-degree scene, but with 3 types of device. So they use the laptop, okay, the less immersive, I guess, the least immersive. And then they also had the tablet, and then they had the headset. So we collected data across UCL and Trinity with all these 3 devices, and we try to have many sequences. Of course, everything is available. And then we kind of had a further analysis of the user behavior with this data set. And then we also wanted to answer a question is, okay, we started from the very beginning on, can we use this analysis to optimize the streaming pipeline? So we also try to see if we could use it or we can see any analogy in that sense. And in terms of dataset collection, we selected different videos. We had 15 videos plus 3 that were tested, that we were watching, that users were watching only as a kind of warm-up video. We tried to consider it as heterogeneous as possible in terms of type of content. Some of them are synthetic, some other are not, some of them are more static, some other are more active, and etc. So the usual bit. We then have 3 types of devices that users were using. Every user was using all the 3, but never repeating the same content. So we were ensuring that all the content were viewed at least by the same number of users, but users were watching always different type of contents. And then we collected the data. Data are, of course, publicly available, and we collected them in the sort of trajectories. So we really wanted to plot all the trajectory over time of the user for all type of contents. Once we had this data, we then wanted to see which type of analysis and understanding we could have from the content. And the first one was, for example, to use, let's call them classical metrics. By classical, I just mean that we didn't use the clustering of before. That comes into the picture later. So we first had the viewport angular velocity, for example, just because we wanted to see at a high level if we could spot some difference. And if you see, here you can see different types. These are the video IDs, but they are subdivided into documentary, action, and movies categories. For each type of video, you see the angular velocity for HMD, laptop, or tablet. So what is interesting is that, for example, the type of content somehow does matter, but also the type of device that you're using does matter. So if you see in the documentary, but even in the action, you see a clear spike for the laptop. So it seems that users were actually navigating more dynamically with the laptop, which might be a consequence of the fact that it is less immersive. So they were less immersed in the scene, and therefore they actually follow less a little bit the scene, and they were more scattering around. That could be an option. But that's one of the results that we have found in this data set. Of course, this is a small one because it's only have 50 users. I mean, it's with the same analogy of other data set, but it would be good to have really huge data set to really understand if you can formalize better this intuition. But this is the first intuition that we saw. We also saw that movie are explored a little bit less than documentary, and this also might be given by the fact that they have a core focus of attention. And so if the core focus of attention is not highly dynamic, it's follow less. This is something that it could somehow be guessed already. And therefore, the first intuition was content, but also the viewing device has indeed an impact on our way of interacting with the content. Interesting, even if laptop, well, first let me explain you what this result is. We then wanted to see kind of the PDF of the viewport center distribution. So if I look at the in the spherical content where I was looking at, you could think about this as a distribution or an histogram, right? So for example, for HMD, you could see that I'm actually navigating more in the scene. So if you look at the overall histogram or distribution of all the angles that I experience, you could see that it's wider than the laptop. So even if the laptop, I was moving more, actually I was moving more, but remaining in a kind of core domain, while with the head-mounted device, maybe I tend to do more drastic movement. So that's also another type of analysis that we had. And last, I described the clustering. Of course, therefore, we kind of formalize the clustering into an affinity matrix that is just looking at the, it just basically translates the number of populated clusters. So for example, is an average of, it is a weighted average of the number of users per cluster. So if you have that users are all very randomly spreaded, it means that this number will be very low because you will have a lot of clusters, but with few users per cluster. While if you have key dominant cluster, this value will be very high because you will have a large number of users for each cluster. So of course, the bigger the cluster, the higher the affinity, because the more similar are the user behavior. And what is interesting is that, of course, depending on the sequence, you get different type of behavior. So in this case, for example, you can see the user affinity, that is this metric that I just showed you, versus time for a given sequences, that is was the baby panda, that is the baby panda camera. So of course, it's not so much of action movie as you can guess. And we can see that we had the user affinity based on the clustering that was done with HMD, the blue one, or laptop, so user with the laptop trajectory, that is the purple, or with the tablet trajectory, that is this yellowish curve. And the red one, the bold one, is kind of the average of the affinity if you just look at all the trajectory together for all the devices. So in this case, you could see that it's very interesting because here there was a scene cut. So there was a kind of big change in the scene, and you could see a drop in the affinity. And that's really because after the scene cut, user restart to wander a little bit around before refocus maybe on the main focus of attention. So you can really see a strong importance of the content and the user affinity, a correlation. It's also interesting to see that at least for HMD and laptop, there is a strong similarity on how the user behavior. This is not the case in another type of sequence that is more action, so a movie sequence, in which is the same type of plot, but you can see that tablet, laptop, and HMD have completely different value of similarity. So it means that in this type of sequence, user can be very similar or very dissimilar depending on the type of device that they use. So that's also interesting because if you, for example, you want to predict the user behavior, you may assume that most of them will have a key trajectory with one device, but there is no point of maybe trying to even have a prediction in an adaptive logic system if they're using maybe a tablet device, because they're really poorly affine. So that's very interesting to see that in some type of sequence, the viewing device does matter. And what we did is, okay, can we then actually try to see a little bit more a use case? So this is quite mathematical, so I will not go into the details of that, but we try to see in an adaptive, in adaptive streaming system in which maybe you have a content provider, CDN, and user with a navigation, an adaptation logic at the end. If we could formalize a little bit, optimize the representation that we store at the server, that is a work that I used to do already in the past. So I was really curious to see how to convert this optimization of the VR representation in these VR settings, and whether we can fetch any information about this user analysis. So the paper goes more into the mathematical details, but I just wanted to give you a hint on what we saw. So the results were mainly at the server side, the store bit rate that still preserve a user quality. So we try to minimize the store bit rate while preserving the quality of the user at the client side. And what was interesting is that if you look at the store bit rate over time for a given video sequence and also the affinity, you kind of tend to have a similar behavior. Of course, it's not exactly the same, but there is a kind of resembling of this, the up and downs of the affinity and the bit rate. That's, of course, something that it can motivate it if you think about it. So users tend to behave similarly. Therefore, you can play a little bit more with the representations. And the idea is that, therefore, this use case was also to show how this metrics as user affinity could be used into a system design perspective. This is the first conclusion of this analysis, that like sequences with no main focus tend to have no perturbation by the viewing device, while the most activity and a focus with the main focus of attention are highly affected by the viewing device. And then in the user-centric use case, we also notice the impact of the affinity metrics could be used as a key metric. And then the last step, let me see the time. Okay, I will try to be short because maybe I will try to use 5 more minutes. We then ask, okay, can we do something else? So that was a clustering. We saw how to use that with the metric and how this metric could have an impact in some system design optimization. Is the clustering the only thing that, of course, we can do? The answer is no. And we also ask ourselves, these trajectories, they can happen in many other domains, of course. So trajectories happen in human trajectories. So when there are human and people moving, there, of course, you already have some trajectories. So is there any other type of studies that has been done with trajectories, and can we bring it into this VR user behavior? And that's what brought us to this recent work. So this is just a preliminary work because it's our first approach of information theory metrics into VR user behavior studies. What we did is, okay, if you take some data collection and raw data collected that we already had, we had some pre-processing just to ensure that everything was consistent in terms of trajectories. And then we wanted to try to use 2 types of information theory metrics. One that was looking at one single user, but for different type of videos, just to try to understand if each users tend to have the same behavior across contents or not. And of course, the other things that we were interested in looking is, if I have a given video, can we have any type of behavior across user? So is the content leading to a specific behavior across users? So the first one is the one that I will be focusing the most, just because I will not have time to go into details of all of this. But information theory starts from the classical definition of entropy. And what we looked at is the actual entropy that is a little bit different. So basically it reflects the frequency of a trajectory that is n steps long, that is already repeated in the past. So it's looking at still the concept of probability similarly to the log similarly to the entropy, but is mainly looking at n, that is the length of a sequence of a trajectory that as a user was already experienced in my past trajectory. And just to give you an idea, a high entropy, it means that I really have a highly random behavior, while a low actual entropy, it means that I have a quite predictive behavior, because in the past I had experienced similar trajectories already. And what was interesting to see is, if you look at these plots, these are like different type of videos that are these ones. And these are all the users. So there are like 57 users that we considered. And basically it's interesting to see that some of them, for example, they tend to have a peak of the actual entropy. So for example, these guys are always with the random behavior, no matter what is the content, while others tend to have a small entropy across the content. So they kind of have a quite predictive behavior, even if the content changes. So that was very interesting, because it means, for example, that if you want to train a neural network to predict user behavior, you may want to train network depending, maybe for user with high actual entropy and separately from user with low actual entropy, or you may assume that user with high actual entropy will not even enter into the picture because the predictability of them is really poor. So you can have many considerations. But that's basically what we showed. And also we showed the difference between the entropy, that is the classical information metric, and the actual entropy, that you can think as the entropy but translating into trajectory rather than just points and an heat map concept. And this is to show that, for example, if you take these 3 users, this one is very low actual entropy, and indeed is quite compact. This is quite spread and it has a high actual entropy. This, it's a little bit more spread than this guy, but for example, the points are the timestamp. So you see that at time 30, 32, 34, 36, 38, 40, it's here. So it's not that it does this jump constantly. Even if it's spread, this trajectory was quite compacted over time. And you could see that the entropy per se is varying, but not critically, while the actual entropy has a little bit more difference. So it's a more meaningful metric to understand this type of behavior. And that's it. This is just the inter-user analysis. So we look at all the transfer entropy. So how much information from trajectory of one user I can infer from the other user. I will not show you the details because it's too long. I just go to the conclusion. So maybe we will have some time for questions. So one is the whole work started by the need of studying and understanding user behavior, mainly for trying to optimize the whole streaming and coding pipeline. First, we identified clusters that were meaningful. So they were really ensuring that users within a cluster were actually looking at the same type of content. And we did that by a clique-based clustering. We then wanted to have a deeper analysis. We collected the data set that was also looking at user across devices, viewing devices. We used the affinity metrics as a proxy of our clustering similarity, and we found out that it's quite useful, and it can also be reflecting some system design metrics. So it could be interesting to also be used for the system design. And this last work is a formalization even further than the clustering to really quantify metric, a number that, however, is taking into account the whole trajectory or part of the trajectory of users, comparing single user across content or for one content, many users. And we're seeing that there are some consistent patterns across different contents. Further investigation, I didn't go into the details, but it's also that the lack of a dominant focus of attention, of course, lead to higher randomness. That is something that we already knew, but with this way, you can highly formalize it, even if that is something that you could already formalize from the heat map, so it's not super new. Further direction, there are many. Here I posted only few. So one is to formalize more the link between randomness of interaction, device, content, and focus of attention. Ideally, it would be really good to work with very huge data sets. These information theory metrics, we want to understand it more, especially now we're trying to understand if we can leverage on this for more reliable user prediction, so the prediction of user behavior over time. And of course, the extension of point clouds, 6 degrees of freedoms, there will be a completely new type of navigation, so that's also part of what we're looking at. And that's it. Thank you for listening.
Thank you, Laura, and let's try to have a virtual applause some way. Thank you very much. This was very interesting.